Let's talk beams. All right, let's get into it. Have you ever looked at a bridge, a floor in a building, or even a simple shelf and wondered, how does that not collapse? The secret hero in most of these structures is the humble beam. Beams are the workhorses of engineering, designed to carry loads across a span without giving up. Today, we're diving into one of the most common types, the simply supported beam. Imagine a plank of wood resting on two bricks, one at each end. That's it. That's a simply supported beam. It's free to rotate at the supports, which makes it a fantastic and straightforward starting point for understanding how structures work. So why is designing a beam so critical? Well, if your beam is too small, it could snap or bend way too much, leading to a catastrophic failure. Nobody wants their floor to turn into a trampoline, or worse, a hole. On the flip side, if you make the beam gigantic just to be safe, you're wasting a ton of material, which costs money and adds unnecessary weight to the whole structure. Proper beam design is a balancing act, a beautiful dance between safety, efficiency, and physics. It's about finding that Goldilocks solution, a beam that's just right for the job it needs to do. In our little engineering adventure today, we're going to design a steel beam step by step. We'll use a real-world example to make things super clear. Imagine we have a 5-meter-long steel beam that needs to support a uniformly distributed load. Think of it as a continuous line of heavy books, of 10 kilonewtons per meter. That's like having about 1,000 kilograms of weight spread evenly across every single meter of the beam. Our goal is to figure out exactly how big that steel beam needs to be to handle this load safely, without bending too much or breaking a sweat. Before we jump into the numbers, let's talk about a few ground rules. First, units are everything. We need to be consistent, so we'll be using meters for length and newtons for force. Second, safety is non-negotiable. In the real world, engineers use a safety factor to make sure their designs can handle unexpected loads. We'll use a safety factor of 1.5, meaning our beam must be at least 50% stronger than what's technically required. We also need to consider the material itself. We're using standard structural steel, which has a known strength and stiffness. Let's get our calculators ready and start building. First things first, we need to figure out how the supports are holding everything up. Our beam is 5 meters long with a 10 kilonewton per meter load. The total load is simple multiplication. 10 kilonewtons per meter times 5 meters equals 50 kilonewtons. Since the load is spread evenly and the beam is symmetrical, the two supports at each end will share the load equally. That means each support pushes up with a force of 25 kilonewtons. These upward forces are called support reactions, and they are the foundation of our entire design. They keep the beam in equilibrium, perfectly balancing the downward load. Without them, our beam would just fall to the ground. Next up, we need to understand the internal forces at play inside the beam. The first one is called shear force. Imagine trying to snap a carrot. The force your hands apply is a shear force. Inside our beam, the shear force is constantly changing along its length. At the left support, it's equal to the upward reaction, so it starts at plus 25 kilonewtons. As we move along the beam, the downward load of 10 kilonewtons per meter continuously reduces this shear force. By the time we get to the very middle of the beam, the shear force is 0. Then, as we continue to the right, it becomes negative, reaching minus 25 kilonewtons at the right support. The other crucial internal force is the bending moment. This is the rotational force that makes the beam want to bend or sag in the middle. Think about bending a ruler. That's the bending moment in action. For our setup, the bending moment is 0 at the supports, since they are free to rotate, and reaches its absolute maximum value right in the center of the beam, exactly where the shear force is 0. The formula for the maximum bending moment in a simply supported beam with a uniform load is M equals W times L squared divided by 8. Plugging in our numbers, we get M equals 10 kilonewtons per meter times 25 divided by 8, which equals 31.25 kilonewton meters. This maximum bending moment of 31.25 kilonewton meters is the single most important number for our design so far. It represents the point of maximum stress, the spot where the beam is working its absolute hardest to hold everything together. The top surface of the beam is being squeezed in compression, while the bottom surface is being stretched in tension. Our job now is to select a steel beam that is strong enough to resist this bending action without failing. This value will directly determine the size and shape of the beam we need. It's like knowing the final boss's health points before you go into battle. Now for the fun part, picking our steel beam. To do this, we need to figure out how much bending stress our 31.25 kN-meter moment is creating. Stress is just a measure of internal force spread over an area. The formula that connects bending moment to stress is sigma equals m divided by s, where sigma is the bending stress, m is our maximum moment, and s is a property of the beam's shape called the section modulus. Think of s as a number that represents how good a shape is at resisting bending. A tall, skinny I-beam, for example, has a much higher s value than a square block of the same weight, making it way more efficient. Before we find our required S, we need to determine the maximum stress our steel can safely handle. Our steel has a yield strength of 250 megapascals, which is the point where it starts to permanently deform. But we don't design right up to the edge. We use our safety factor of 1.5, so the allowable bending stress is 250 divided by 1.5, which gives us 166.67 megapascals. This is our safety limit. The stress inside our beam must not exceed this value. Now we can rearrange our formula to find the minimum section modulus we need. S required equals m divided by sigma allowable. Let's do the math, but first watch the units. Our moment is in kilonewton meters, and our stress is in megapascals, which is newtons per square millimeter. Let's convert everything to newton millimeters. Our moment, 31.25 kilonewton meters, becomes 31,250,000 newton millimeters. Our allowable stress is 166.67 newtons per square millimeter. So, S required equals 31,250,000 divided by 166.67, which is 187,500 cubic millimeters. This is the magic number. We need to find a standard steel beam with a section modulus of at least 187,500 cubic millimeters. In real engineering, you'd look this up in a steel manual, but for our example, we'll design a simple rectangular one. Let's design a rectangular beam. The formula for the section modulus of a rectangle is S equals B times H squared divided by 6, where B is the width and H is the height. There are infinite combinations, so let's make a practical choice. A good rule of thumb is to make the height about twice the width, so H equals 2B. Substituting this into the formula gives us S equals B times 4B squared divided by 6, which is 4B cubed divided by 6. Now we set this equal to our required S4B cubed divided by 6 equals 187,500. Solving for B, we get B cubed equals 281,250, which means B is about 65.5 millimeters. Let's round that up to a nice practical number, say 70 millimeters. If B equals 70 millimeters, then H equals 2 times 70, which is 140 millimeters. So we've selected a 70 by 140 millimeter rectangular steel beam. We've chosen our beam, but we're not done yet. We need to run a few final checks to make sure it's up to the task. First, let's double-check the shear stress. Just as bending moment creates bending stress, shear force creates shear stress. For a rectangular beam, the maximum shear stress occurs at the center and is calculated with the formula tau max equals 3 times V max divided by 2 times A, where V max is our maximum shear force, 25 kilonewtons, and A is the cross-sectional area of our beam. Our beam's area is 70 times 140, which is 9,800 square millimeters. Let's plug in the numbers. Remember to convert kilonewtons to newtons, so V max is 25,000 newtons. The formula becomes tau max equals 3 times 25,000 divided by 2 times 9,800, which is 3.83 newtons per square millimeter, or 3.83 megapascals. This value is extremely low compared to steel's shear strength, which is typically around 0.6 times its yield strength. so our beam is perfectly safe against shear failure. In most steel beam designs, bending is the critical factor, and shear is rarely the cause of failure unless the beam is very short and deep. But a good engineer always checks. The last and very important check is for deflection. We don't want our beam to be a diving board. Excessive sagging can damage finishes like drywall or tiles and just plain looks unsettling. The allowable deflection for this project is specified as the span length divided by 360. So delta allowable equals 5,000 divided by 360, which is 13.89 millimeters. Our beam cannot bend more than this amount. The formula for maximum deflection in our case is delta max equals 5 times W times L to the fourth divided by 384 times EE times I. Here E is the modulus of elasticity, which is 200 gigapascals for steel, and I is the moment of inertia, which describes the beam's shape-based resistance to bending. For our rectangular beam, the moment of inertia, I equals B times H cubed divided by 12, which is 70 times 140 cubed divided by 12, giving us 16,006,667 to the fourth power millimeters. Now for the big calculation, delta max equals 5 times 10 times 5,000 to the fourth divided by 384 times 200,000 times 16,006,667. After punching that into a calculator, we get a maximum deflection of 25.5 millimeters. Our calculated deflection of 25.5 millimeters is greater than our allowable deflection of 13.89 millimeters. This means our beam is strong enough not to break, but it's too flexible. We would need to go back and select a deeper beam with a higher moment of inertia and then rerun the checks. This iteration is a core part of the design process. It's all about finding that perfect balance of strength and stiffness.